Conditional logical operator. The conditional logical operator is represented with the symbol arrow. Or sometimes the simple English word implication can also be used to represent the conditional logical operator. Let's look at the definition of conditional logical operator. Let P, Q be two propositions. The proposition if P then Q is denoted by P implies Q. This is called as a conditional or an implication statement. Now let's try to understand the meaning of if P then Q. If P then Q means if P is true then Q is true. Whenever P happens, Q will happen. It means P is sufficient for Q to be true, but it does not mean P is necessary for Q to be true. Let's try to understand these statements with the help of an example. If the bus is late, then she will not come for work. This statement is in the form of if P, then Q. If the bus is late, then she will not come for work. That's what we mean when we say P is sufficient for Q to happen. But sometimes, even if the bus is not late, she will not come for work. Maybe she is sick, or maybe she is having some other appointments. That's why we say P is not necessary for Q to happen. Let's look at one more example. If you eat good food, then you will not be sick. This statement is in the form of if P, then Q. If you eat good food, then you will not be sick. That's what we mean when we say P is sufficient for Q to happen. But sometimes, even if we eat good food, we will be sick. Maybe because of something like coronavirus. Even if we eat good food, we may be sick. That's why we say P is not necessary for Q to happen. Now let's try to understand the truth table of conditional logical operator. P, Q, P implies Q. If P is true, Q is true, then P implies Q will be true. If P is true, Q is false, then P implies Q will be false. If P is false, Q is true, then P implies Q will be true. If P is false, Q is false, then P implies Q will be true. Let's observe these values. P implies Q is false only when P is true and Q is false. This truth table can also be generated with the numbers zeros and ones. If P is 1, Q is 1, then P implies Q will be 1. If P is 1, Q is 0, then P implies Q will be 0. If P is 0, Q is 1, then P implies Q will be 1. If P is 0, Q is 0, P implies Q will be 1. From this table of zeros and ones, P implies Q can be mathematically defined as P implies Q is equal to 1 if and only if P is less than or equal to Q. This formula can be verified for the values given in this table. 1 implies 1 is equal to 1 because 1 is less than or equal to 1. 1 implies 0 is equal to 0 because 1 is not less than or equal to 0. 0 implies 1 is equal to 1 because 0 is less than or equal to 1. 0 implies 0 is equal to 1 because 0 is less than or equal to 0. That's why we say P implies Q is equal to 1 if and only if P is less than or equal to Q.